Good evening, all. Am I audible to you?
Yes,
Yeah,
yes,
thank
ma'am.
you,
Yes,
sir.
ma'am. You're audible.
Yes,
Okay,
ma'am.
sir. Good evening, professors and as research scholars. Um, Today's session is all about decoding your quantum data, along with how are we going to integrate quantum and AI for the upcoming or real world applications. So the objectives for today are, so we are going to understand what is the relationship between the AI and quantum computing. And then we will explore how quantum computing enhances the AI for data analytics. And we are going to learn, see two or three case studies, how this AI and quantum computing can be integrated. To start with, so you're in the day 5 of this FDP. So most probably you must have got the fundamentals of this quantum computing. But to start with, and as an introductory or recall note, I
Good
would
evening,
like to tell.
ma'am. Sorry for the interruption, ma'am.
Yes, sir.
Ma'am, we would like to introduce you first, so
Oh,
that it will
sorry,
be
sir. Okay, sir.
the audience will be familiarized with you before
Okay,
starting.
sir. Do I
Actually,
should
yeah,
I
yeah, yeah.
introduce myself, sir?
No, no, I'll do it, ma'am. I'll do it, ma'am.
Okay, sir.
Welcome,
Okay, sir.
participants.
Thank you.
Actually, we were testing, but ma'am continued the session. Thanks for that, ma'am. Uh,
Thank you, sir.
o- o- okay, participants, welcome you all for this again day 5 faculty development program on quantum intelligence, AI, quantum convergence in cyber defense and space technologies. And we are happy to have you all again for this beautiful session. And today we have Dr. K. R. Sri Preetha, Assistant Professor, Senior Grade G2, Grade 2, School of Computing, VIT Velur. And the topic which we are going to cover today is decoding the quantum data universe, AI for insights, interpretation, and innovation. Dr. Sri Preetha KR is a multidisciplinary researcher, specialization in AI, machine learning, deep learning, computer vision, and IoT. Her works includes advanced model of for healthcare diagnostics such as kidney stone detection and PCOS detection, as well as real-time crack detection, structural defect analysis, and UAV-based inspection for smart infrastructure. She also develops IoT driven predictive systems for environmental monitoring and energy analytics. With expertise in developing AI on edge devices, her research is strengthened by international collaboration across South Korea, US, China, and South Africa, reflecting a strong profile in AI enabled healthcare and intelligent infrastructure. So, we have a very strong resource person today, and hope the participants will definitely enjoy the session. Ma'am, over to you, madam. Thank you. Madam, ma'am, am I audible, ma'am? Preeta, ma'am?
So you're audible.
I don't think what's the problem is. Preeta, ma'am, please unmute your mic, ma'am.
Sir, I guess I'm audible now.
Yes, 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 ma'am. Yes, ma'am.
Awesome.
Please, ma'am. Please.
Okay, sir.
Thank you.
Okay,
Thank
sir.
you.
Thank you, sir. Thank you for the introductory note, sir. And to introduce about me, I have been doing my research in South Korea for past 3 years, and I have collaboration with professors across 4 countries. And during this research period, I got an opportunity to work on multiple domains, especially on structural and civil engineering, and then my thing broadened to biomedical also. So with this introductory note, let us move on to this topic for today. And quantum computing is gaining its popularity over AI nowadays. So when we consider about a decade back, we were all learning about what is ML, DL, computer vision technologies, and now we have moved on from. We are not moving on. We have in a what is it? We have improvised to a new concept of this quantum computing. So we have a near future with this quantum computing, and now we are in the path of, we are taking a baby steps, and we are sure in near future we will be doing a lot of things with this quantum computing. So what is this quantum computing is all about? Why we need this? The quantum computing, the traditional computations works on a bits of data, say zeros and ones. But this quantum computing has led its a new era of including the mechanics of the science, how the atoms and particles work on. So from normal rules, now we move on from classical computers where we store the data into bits to qubits. In quantum computing, two things are most important words, buzzwords. One is superposition, the next one is entangled. So I hope you all know what is superposition. So let me give the difference between the qubits and bits. In classical computers, the information we store in bits, say zeros and ones, either on zero or in one bit we do it. But whereas in quantum computing, we use both zero and ones for computation. So this is that both 0 and 1 at the same time, so that we call it as a superposition. So whether we do an kind of manipulation or storage or any kind of processing, now we consider two states, 0 and 1. And now, what is quantum analytics all about? Quantum analytics helps in processing and analyzing a data in ways that we are not possible before. The quantum computers are helpful for handling complex calculations much faster than the regular computers. Why? Because since we have used only the states of 0 or 1 in traditional computation, the processing speed is much lower. But whereas in quantum computing, as we are using the entangled, the superpositioned bits, so qubits, we have a computational power, parallel computational power, so that the space and also the computational facilities are being increased. So it is like having a super powerful computer that can analyze vast amounts of data and find patterns or solutions more quicker than the traditional methods. So quantum analytics uses special algorithms. So what kind of algorithms? Normally we in traditional data analytics or predictions or ML, we have used SVM, support vector machines, k-means, anything you use, any algorithm you name in ML, all those can be now upgraded to a quantum machine learning languages. So what makes the difference here? Let us assume that in a traditional machine learning language, what we do here is, first thing, we take our data, represent it, and then it might be a tabular data. So initially we were been starting with the data analytics on an Excel sheets, where manual accountants can able to see what is the pattern of the data, how actually the transactions and flows goes on. And later it is being expanded to Excel sheets with mathematical models. And then later, as the data increases, the machine learning languages comes into picture, algorithms comes into picture. So what makes the difference is we have automated the analysis using some algorithms. So now the data has increased, the algorithms again learn the pattern in the data itself. And when the data representation changes, when we get into unstructured data or variety of data, so what we have done is we have migrated from the traditional mathematical models to ML and then to, say, deep learning algorithms. So here what difference is made is the data is the same. Okay, the algorithm is the same. And now only the size of the data increases. So now what happens from hundreds to thousands and from thousands to millions and billions, and now it's increasing exponentially than the human brain have thought about it. Now what we require is more computational power, quicker computation, and then cost effective one. So whatever the improvisation we have made through through the machine learning languages or AI is all about the algorithms, okay, and all about the datas. But there are limitations on it. We don't have all kind of things to be done only with the ML and DL algorithms. What do we require? We require some new strategy so that the computational powers are being increased. So we do it in a faster mode. And the next one is the space should be used very effectively, efficiently, and the accuracy. Yes, it is most important. So for that reason, we get into quantum computing. So this how does this analytics, quantum analytics will help us when the attributes of our input increases exponentially and the data increases exponentially. The ML algorithms will stuck up at one position. So what we have to do? We have to increase the representation. So quantum analytics will help us to analyze the attributes in multi-dimensional space in a quicker manner. So we optimization, when comes to optimization. So what is optimization? We are trying to make some algorithms to do the best in a quicker manner. So in traditional AI, what we do is we do tune the hyperparameters. I hope everyone is aware of what is high optimization and hyperparameter tuning related to deep learning algorithms. When I want to bring the best out of an algorithm on some data set, so what we do is we try to optimize that particular algorithm for the data. Here, optimizing means we take up n parameters. Say it might be if you take on k-means algorithms, we have to choose which would be the best k value to make the best out of the given data and the algorithm. When it comes to CNN models, neural networks, we would like to think about what would be the parameters, say epochs can be one, and what would be the optimization models and etc. How many layers we use, what are the strides. So these are a few parameters we keep on tuning so that we get the optimized result. So here in traditional algorithms, we don't have any methodology to optimize your hyperparameters. What you do is even you go with some optimization techniques. Again, what they do is they take the combinations of the given parameters and then try to fit in the best output from the combinations. So here the computational power is too large, but here the quantum analytics helps us to do it in much faster way. How? Because we represent it in terms of qubits. We represent it in terms of qubits. Say, supposing I have 1 qubit, then it means 0 and 1. I have 2 states. If I increase my qubit to 2, it means 2 power 2. So I have 4 states. So when I keep on increasing my qubits, so what happens? My space at a time, it gets increased. So I can effectively save the data and I can effectively compute it in a parallel manner. So that what happens, you can get the best out of it using a parallel computation in a shorter period. So that is why we go for this quantum analytics. So quantum analytics are really very helpful when in the place where data's increase in volume, data's increase in variety, and also the veracity. Because in real time, we get data are being generated from different sources in different means, and we cannot. It is an unstructured data. Fine. So in the near future, if we want to strategize something that is related on a data, then quantum analytics is more important. And now to get into AI. So what is AI? You all know. Why we use AI? We use AI to learn something, to reason out something, to make decision, and also in pattern recognition. So how AI helps in handling huge volumes of data? First thing is it can process a maximum amount of data more quickly in millions of records are being stored up in one place, and you use algorithms to uncover the underlying knowledge or underlying pattern, and you grasp whatever that is required for a particular application, and then we tailor it. Fine. So machine learning algorithms we have used, deep learning algorithms we have used, and now NLP is gaining its popularity when people want to communicate across the world using different languages. What is the commonality that they can do is they can go for NLPs, where you can mainly go for translating your languages from one to another. So this is very, very, what to say, an attractive research that is being actively around the globe. That is NLP processing. That is the translation of one language to another language. Still, though we have an n number of translators, but precise and accurate translations are not yet. We haven't reached it. So NLP popularity across the globe, mainly among the young researchers. And so I was working on structural health monitoring in my previous lab, where I have come up with more simulations using AI models, like finding the damages in steel structures, and finding the spalling, detecting or predicting the spalling of walls. And also, since I have worked closely with the robotic robotic, structural, and civil engineering, most of my research works are related to civil engineering. So the few of my research works I have presented here. The first one is all about finding the cracks on the buildings, and then a concrete spalling. It's nothing but you can see that the walls might fall off when there is a high humidity in the walls. Okay, and then structures. See, these were all real-time applications we were developed when this is pertaining to the requirements of the South Korean society. So since this Korea has high-rise buildings all everywhere, their planning of city building is completely of high-rise buildings. So you can see that the tall buildings need more maintenance. So they have a lot of issues in doing these maintenance manually. So they have invested a lot in integrating AI and the structural health monitoring. So few of what we have worked on, I have presented here. So the first one is the all about this structure, damages in the structural. It may be a wall, it may be a steel, or it may be a road. Okay, so we have automated certain AI models to learn about what is the severity of the damages, and what would be the immediate remedial action that can be given, and the supportive systems and recommendation systems on all those things we have done. And also, since South Korea is prone to earthquakes sometimes, back in 2009, they faced a very severe earthquake, and then people started moving towards the earthquake-proof buildings. Okay, so before they start a building, they go for and got a soil test called as liquefaction. So where they test the soil after the occurrence of an earthquake, and they find whether this particular soil is fit enough for construction buildings. So these are all few we have automated, and similar we have given an AI based model to check on all these data and analyze whether to test the suitability of soil. So such many things that we have earlier seen. Okay. And I would like to elaborate two case studies where we have used AI, and later on what are the limitations we find it, and what can be done to make improvise or move it towards the quantum AI. The first case study I have taken is to find the surface cracks in high-rise buildings. So this is say when we have buildings, say when it ages, we can see minute as well as hairline cracks and also severe cracks appears on the structures of the building. Sometimes it may not be fatal, but many a times when the height of the building keep on increasing, so and the age increases, this becomes a threat to the people who live over there. So yeah, periodic maintenance are required. So what they do is they try to manually inspect it. And nowadays, with the help of drone technologies, we try monitoring these high-rise buildings where people cannot move on and see to it. We have used these drones to find or capture the images or videos of the walls so that it can find the cracks, whether the appearance of cracks appearance is there or not. And this is not that easy one actually, because even if you have the drones over there and it has to occupy, it has to cover all the areas, and also the cracks may be severe cracks also may be minutely visible. So there comes a challenge for us to check on whether the data what we are procuring is precise or it is accurate, etc. So for that we have assembled a drone with a lot of sensors, and also here the drones capture the videos, and then after the complete inspection of the building we retrieve the videos and then check for the cracks, and we apply some some deep learning algorithms to check on whether this particular frame has a crack or not. But that doesn't make sense, because when you explore a large area, the decision has to be taken then and there. For that reason, we have developed an transfer learning model using um, actually we have used EfficientNet, and this has been implemented around 2017. Okay, so by the time the transfer learning was in boom, so what we have done is we have developed a very lightweight model, and then integrated with this UII. So what happens is, and then we have connected it to an ground station. So as this UAV moves, this drone moves up, it captures the videos. And with the instantaneous live video, what we have done is we were able to find the cracks. And also it can able to say what kind of crack it is and what is the percentage of that accuracy. So all these things will be in a live feed. We try to get it, and also we locate it with the altitudes and latitudes. So this made us very easier for us to check on whether the cracks are available or not. And uh, so you can see that with the distance and with the lights, we can see that whether the cracks are available or not. This is the result that we have taken. And now you can see this. This is the general view of the building where we have gone for this testing. And when supposing, what are the limitations you can find it over here is, first is when the area increases, I cannot go on by using only one drone, okay, at a time. If the area increases, one drone is not enough for me to inspect it. So for that, I have to go for multiple drones. And if I go for multiple drones for the live data and file, the live decision, I have to coordinate all these drones, and they also provide multiple data at a time. And these data has to be synchronized and given to an machine learning algorithm. Okay, so what would be the what would be the burden for the system is, you generate more data, instantaneous data, and you need an instantaneous decision. But the computation is not that easy with deep learning algorithms. It's slow. Actually, the decision making is very, very less. The performance is very less when it gets integrated with multiple drones. I mean, the data are instantaneously flooding the language. The algorithm. Yes, it shows a very poor performance. So now, to improvise over this, quantum computing can be used. Why? Because now when we use the quantum computing, our space is increased, the computational space is increased, it is parallelly computed, and the decision making would be much faster when then compared to that of the machine learning algorithms. The second work that what we have done here is in South Korea, as I mentioned, people do this maintenance work all through the day. Okay, especially they do it at the night time. The all maintenance works are being taken care during the night time so that they don't disturb the public. So construction workers, when they do it, they are very particular about, first is they are the country is very particular about the safety of any citizen. Okay, so when this there is a threat for the construction workers, since they work almost in high-rise buildings, and during the night times, the safety precautionaries is made mandatory. The government has insisted the safety of the workers is the primary task. So for that reason, we have they want to monitor the construction workers, whether they are following the safety precautions. So here we have taken few safety precautions like wearing a helmet, wearing the goggles, gloves, okay, and then their safety belts, and what is the position on which they are climbing, working at the heights. All these parameters we have taken into consideration and developed a model which will tell you on seeing a particular, yes, sir. Sir, can I continue?
Sure.
Sorry, sir, am I audible?
Yes, ma'am, you can continue. Yes, ma'am.
Okay, sir.
Yes, ma'am,
Okay,
you.
sir. Okay, sir. Okay, sir. Thank you. So these were all few considerations we have taken, and then we have implemented a machine learning algorithm for detecting whether the person is wearing the helmet or not, whether he is using the gloves, at what whether his posture is safe posture or not. So here the problem is initially that is the data is not available. So what we tried is we created a data using thermal camera. Why? Because this has to be a generalized one that can be used during the daytime as well as during the nighttime. So we used thermal cameras for creating the data set, and because it is a generated version of it, we were not able to produce more number of data, so we went for data augmentation techniques, and then we went for detection algorithms. Why? Because we have to check on whether we have this helmet or not, whether he is in a safe position or not. So what we have done is we have labeled the each and every frame of the video, and then implemented the algorithm, and then now we are able to show off whether what is the condition of the person, whether he is in a safe position or not. Okay, so this was quite fit in, and we have integrated this into a surveillance camera. So what happens, you need not go for a separate system to check on whether the person is working or not. If it is being transferred into a surveillance camera, so when it captures, what happens is it just gives you the alarming messages, and then messages to the managers, so on. So this is how the product has been developed. And now the limitation of this particular model is, so you can see that in the data set that we have developed, we have single persons all over. So that means when you have multiple people, how does it works? When I want to monitor the entire building, the entire area, in that case, I would have installed the same model in different surveillance cameras. So how am I going to integrate all these videos, and all these videos together has to be processed by a deep learning algorithm? There comes a computational glitch. It's not that easy, it's not accurate, and the performance is not faster. Now, this has a scope of upgrading it into an quantum analytics. So this is a place where we want to integrate AI along with the quantum computing. So for insight, let us compare the traditional AI with the quantum AI. First, in traditional analytics, what we do is we collect a data. The data might be from different sources. It might be different sources, like it may be from applications, it may be from multiple sensors, or it may be you might be working on across different databases, so etc. So anyway, in traditional analytics, we will collect the data or create the data. The data that we have collected or created may not be in a format which is fit enough to apply to an ML or DL algorithms. So what we do is we pre-process it. We prepare the data according to our requirement. And once the data has been prepared, what we do is we would try to find out which is the prominent feature that would serve as an input for our required or expected output. So we do feature extraction, and for feature extraction, we use n number of algorithms which would perform better on different algorithms on different kind of data. There is no generalization. And then based upon the attributes that we have taken, we will select the model, and model selection also becomes a chaotic thing. The only thing what we know is regression, classification, and clustering. These are different ways, that is the different machine learning categories. But among them, we have multiple algorithms. So we have to choose on trial and error method, which is the model that we are going to use it. And then at present, when the data increases, we are now provided with cloud GPUs. But previously it was only CPU. So when the data volume increases and the complexity increases, now we are depending on the GPU for computational. And when this particular model executes, we are not sure how long will it take. It may run for hours, minutes, based upon the size of the data, based upon the nature of the data. Sometimes you get your results in few hours. Sometimes it executes even on GPUs. It takes days to learn or train the data. Fine. So what happens here? We are not, the time we take, or the time or the speed of computation is being slowed down when the data gets increased. So this is a limitation we find when we work on this traditional analytics. And now let us, how the quantum analytics will help us. So when we collect the data, it will be a classical data. Normally, whatever we collect is a classical data. Now what we try to do is we will represent the classical data into the quantum states. So for that, we can use the encoding techniques. Okay. So then once this is being converted, now what we do is we try to do the feature extraction. So feature extraction also, we have certain methods that we can use it. Okay. And then they're all related to quantum. So it's the algorithms has to be redefined so as it can work on with the quantum data to extract the features. And then the model processing, where we have quantum SVM, quantum CNN, quantum vector evaluation things. So we go for a different kind of algorithms, which is not new, but we are enhancing it, or we are trying to make changes to the existing algorithm so as to support the quantum data. And quantum compute, the computational here is also made as parallelism. So here it comes. Here, let us see the difference between how the computation of the traditional and the quantum takes place. So in traditional algorithms, so how the training takes place is you fix the parameters. Once you fix the parameters, and for that particular parameters, hyperparameters, the model gets trained. And after the result, after you test and get the result, you might find that you are not compromised with the result. And then again, what you do, you just change the hyperparameters, and then you refine it, and then you go for retest. So that's how we do, or we try to include an optimization technique so as again, the algorithm by itself finds the, hypertunes the parameters and comes up with the best one. So for that, whatever the algorithm or method we have implemented, it's not parallelly computed. It is done sequentially. So for each sequential steps, sure it will consume more time. But when as you use the quantum computation happens across a multiple states at the same time because of superposition. And so the analysis will be more faster and the predictions can be done, and it's quicker when you compare to that of the traditional machines. And also when you take the results, you will get the meaningful results. Why? Because you have different states, and you all the optimal solutions are being produced at the same time, you can find more insights from the results. So that the decision making is precise in real time, quicker, faster, and efficient. So that's the difference between your traditional analytics and your quantum analytics. So where do we intersect the AI and quantum computing? The first is the faster computation. So when compared to that of the classical systems, so when traditional AI takes a long days or weeks to process a large data, but quantum can dramatically reduce this with finding the multiple possibilities at a time. Example, we can take a drug discovery. So classic, what is drug discovery is you try to give a drug to a patient. Okay. And in that, the medicine, what is the combination of the medicine that would help to overcome the disease is what the AI models are looking for. So in drug discovery, they try to find the fusion pattern between the medicine and the existing cell. So it perform. What happens is we in AI we try to simulate and produce different molecules on interaction that we are trying to automate. Why? Because when you go for wet labs in biotechnology, when you go with wet labs, it will take weeks and months for you to create a small data set. So now the people are trying to simulate it with the help of AI. So the basic idea is when you give a drug to a cell, maybe a defected cell, how does this how does this medicine gets interacted with this particular cell, and what are the patterns that it can produce? So based upon the pattern, they predict whether the disease is curable for this particular drug or not. So when we use this with traditional AI, sure, it will take more time, but if we convert it into and quantum computing, then it can simulate molecular interactions faster than that of the traditional AI. So this will help us to develop more new drugs and treatments. And now Google's AI team is working on this. And the next one is ability to process large and complex data sets. As I mentioned, when the complexity of a data set increases, what does the complexity means? When the number of attributes increases, when the number of when it is multidimensional. By the time the traditional algorithms will not help you to process the attributes at the same time. So we into this quantum computing, as it produces the parallelism. Unlike the traditional bits, the qubits have a quantum computing so that it can take multiple states and superposition at once. So what happens? It enables faster data analysis, and also even the pattern recognitions are being done very easily. So in near future, if you have financial institutions which are using AI for risk modeling and portfolio optimization, now they can move on to quantum systems to evaluate simultaneously, giving faster and more accurate insights on the investment decisions. Why? Because now, since we are being connected globally, and financial institutes are making use of each and every person's data, and then they are trying to give possible solutions. So personally, if you are being connected with any of the financial management industry, you can find the difference. So people, when you go for consultation, people will have the data with where they will be analyzing your financial status, or strategizing is based upon the database that they have, and something globally. Okay, but it is not interconnected with n number. If there is a repository and if that person can get connected with across the globes, and the computational power is also quantum based. So what happens is they can easily give you an very accurate strategy or accurate insight about what to do and what not to do. Fine. And then the optimization problems and pattern recognitions are more very easier one. As I mentioned, genetic algorithms can be used for pattern matching and optimization. For optimization algorithms, normally we use genetic algorithms, but these algorithms can be slow and inefficient when it deals with a large data set. On quantum computers, these can be solved more efficiently with the help of some algorithms like quantum approximate optimization algorithm or route optimization. For example, you can apply this on the logistics. Route optimization in the logistics. So the companies use AI to optimize the delivery routes, considering the distance, traffics, and fuel consumption. And also, as the number of delivery point increases, the optimization problem becomes exponentially complex for these companies to handle. Where if you use quantum enhanced AI, okay, then you use multiple potential routes, and that can be easily or simultaneously they can be assessed, and it can give you an optimized route in no time. So these are a few things which helps quantum computing over enhancing this AI. It's AI and quantum computing is not separatable. AI is being improvised with some space and also computational power with quantum computing. So that is the concept over here. So we have a number of real-time systems. One is the autonomous vehicles, which is now gaining its popularity across the globe. And you all know we are trying, the automobile industry and also the AI industries, everyone is moving towards this autonomous vehicle, creating an autonomous vehicle, which can take decisions in real time, navigating the traffic or decision making, speeding up, slowing down, and optimizing their driving routes, everything by itself. And climate modeling, since each and every part of the world is experiencing this climatic change, and they want to give and global wise what to say solutions or the strategies to reverse this climatic change. Global warming, yes, we are trying to reverse. So the governments of different countries are strategizing and coming up with a n number of methodologies, but still analysis makes a point. So if you get a good if you get a precise analysis, and then you can strategize. So for that, people need to access the data across the globe, which you cannot imagine. So a lot of data at micro level and macro level data are being flooded in even in seconds. And how does this can be handled? What is the usage of this data? How do we recover the knowledge out of this data? With the basic AI, ML, deep learning algorithms, this is not at all possible. So the analytics, we have to bring in the quantum so as you expand the dimension, you expand the space of exploration so that the parallelism and computing can be increased. So quantum AI in climatic change, climatic modeling would be the best case study we can ever take it. And there are a number of research. There is no concrete solution for any of the applications I have listed over here. Theoretically, we are trying to include the quantum computing along with the AI. So this has to go hand in hand. Whatever the evolution that we get in AI, that has to be implemented along with the quantum computing. So the basic idea is the data that what we get or that what we generate or classical data, this has to be converted into the quantum representation. And then our algorithms has to be modified, or it has to be customized so that it can be applied to a large data that access the quantum data. So this is how an AI can be shifted. It's not shifted, it has to be hand-holded towards the quantum computing. Sir, do I have time?
Yes, ma'am. Yes, you have, ma'am.
Yeah, okay, sir. Thank you. So now let us see few examples how AI and quantum computing can be used. So this, if you are doing some research, and this case studies would give you valuable problem statements, because we have a lot of trajectories in this use cases what I have taken. So each and every challenge, or each and every point that we whatever we find it as a limitation is a scope for development. Okay, so in autonomous vehicles, so you all know what is an autonomous vehicle. Real time, we are trying to move the vehicle, making driving decisions by the system itself without the manual intervention. So in this case, here in the autonomous vehicles, the environment is completely dynamic. Before we move on, first I'll just tell you what is the scenario is all about, and then let us compare what have to be done to make this system a successful one. In the autonomous vehicles, we have n number of sensors that are being connected to it. Say lidars, so which is used for sensing the distance between different objects in the dynamic environment. The camera feeds the GPS signals, your traffic information, and the maps that you are connected. All these are all inputs that is being given to the particular vehicle that is being that is autonomous vehicle. So these are all massive sensors that is being integrated onto the device, onto the system. And if you use AI models, so what happens is, what is the expected thing that expectation of our real autonomous vehicle? The vehicle has to move in a correct direction, in a safer manner. It has to take decisions when dynamically, if any of the that is respective to that of the dynamic environment. For example, if there is a possibility of a collision, or you have some obstacles in between. Okay, so for all these things, it has to make some it has to make some decisions so that it it drives safely. So optimal decisions in a quicker time, without no delays, and without compromising safety is our expected output. Is this possible with AI? The present time AI? Yes or no? No. The thing is, because we are including n number of sensors, and these sensors has to communicate with each other or with the modeling system, and to make decisions, and these decisions has to be taken very quicker, in very quick, right? So are these things are available in the present world? Is it easier to implement it with AI? Have we reached 100% of it? No, not yet. So for this, you can move on from traditional AI to an quantum AI. So what kind of analysis we have to do? So in real time, the processing raw data and the dynamic inputs to detect the objects, road structures, and dynamic elements. This is the first one. And the second one is we have to concentrate on motion analysis. That is, what are the surrounding vehicles we have? Is there any pedestrians? Is there any cyclist moving around on a non-probabilistic models? So what you have to do is, you should know what is the motion analysis should be there in and around the vehicle, in every instance. So these are all instantaneous data. And then based upon these perceptions, what you have to do is, you have to create a route map. we have to compute, that is, you have to compute a safest and also the fastest path under these constraints. Say you have a traffic, you have some road geometry, so you might have an speed breaker in between, or you might have a pothole. Okay. And there might be an obstacle. It may be a static obstacle, or it may be a dynamic obstacle. So based on that, it has to fix a route. And then for that route, it has to be optimized one. So a path planning is more important. And then next one is the risk assessment, evaluating multiple driving actions. We have to select the one with the minimum risk. So decision making is more important. And also it has to check on with the multi-agent. So what is multi-agent is not only our car is an autonomous vehicle. In case you have multiple autonomous vehicles traveling on the road. So what you have to do is you have to coordinate with each other. So your UAV would be one agent and the other one would be another agent. So these two agents has to interact so as they drive safely, they choose an optimal path and also the fastest mode. So these are all the things that you have to analyze when you create an autonomous vehicles. How to solve this? So traditional AI in autonomous vehicles works by breaking the driving task into three main things. One is perception, and the next one is prediction, and then the planning. So if or each and every stage we use different algorithms to interpret the environment and to make the safe decisions. So in the perception layer, yes, perception is nothing but receiving or learning the environment. And in the prediction layer, we use the object detection algorithms and models to check on what is the object and what is the trajectory of its motion, and how, supposing if it is driving in a lane, and if the cars has to change the lanes, and how the pedestrian crosses or how the traffic flow intersects, all these things has to be predicted. So for that we should develop, or we should integrate the ML models. Okay. And so if I want, this is all about the first layer. Next thing is, if I want to implement this using an AI algorithms, computation power comes into picture. How do we compute it? So as I said, we all know driving a car needs an quicker decisions, faster things. Are we supported with that kind of computational power with the UAVs? Is that easier to introduce it to a common man? Is it easy to use it in the real time? No, it's not easy. We need GPUs. The GPUs, again, it's an investment on hardwares. When the environment becomes more dynamic and complex, yes, it gives you a lot of data and dynamic data, and those data need to be processed and then fed into GPUs. So when you think about the computational power, and it's not easy with the algorithms and also computation and also the spaces. So this is a limitation of any traditional AI. So first one is the combinational explanation. That means the path planning requires evaluating exponentially growing state spaces, and classical solvers really struggle with it. And with the computational latency, you can see the deep learning models will create a large matrix multiplications, which will normally slow down your, will slow down. And there is no point in connecting with the cloud and improvising the methods. That's not possible. Okay, so what we can do is you can include the quantum computing into the traditional AI algorithms. So for perception, you go with the quantum. So what happens, whatever the input signals you get it, you have a space to project it in different spatial notations. And if we want to find the combinations of this, is you have a parallelism in quantum computing, so that all the combinations can be computed in faster mode, so that easily you will get the best path. And among the different paths that has been generated, you can use any kind of optimization techniques using quantum algorithms, so that your path planning is easily given. And also reinforcement learning, you can also introduce reinforcement learning with quantum computing, um, for faster convergence and optimal driving strategies. So, with this, I stop. And so there are a lot of, I can say that there are a lot of case studies which includes where you can extend the research work with integrating your AI with quantum. So whatever things that we have implemented so far with this AI, but and find it which can be improvised using quantum. These are the scope of expansion in the research area. So with this, I conclude my session. I hope this would have given you an insight of what can be made to integrate quantum along with the AI algorithms. Is there any queries? I'm happy to address it.
Participants, if you have any queries, please ask to Madam.
Okay, sir. Can I? Okay, sir.
Participants, do you have any questions? You can ask. Participants?
Okay, sir.
Ma'am, I
No
think there is
issues.
no. Okay, ma'am, I think there is no questions from the participants, ma'am.
Okay, sir. Okay, sir.
Thank you, sir.
Thank you
Thank
for
you so much
giving me
for.
the opportunity to interact. I mean, to share the knowledge that I have gained through my research thing. My special thanks to Panimala College and the Atal organizing team for inviting me for this wonderful session. Hope there are a lot of takeaways from this FDP, and because the research is now focusing on the quantum computing, and this is an young and also the young research area where a lot of improvisations are being looked forward. And let's learn together and grow together. Thank you, sir. Thank you so much.
Okay, thank you so much, ma'am, for sparing your valuable time.